All right, problem 4, Unit 11, electric fields and forces. So, use the force, young Padawan. Use the electrostatic force between two charges. All right, we have an electron. And it is being accelerated. It's placed in an electric field with this magnitude, newtons. And you notice the newtons per coulomb. Okay, newtons per, what the heck's going on? Newtons per coulomb, and that's the strength of the force. So we're also going to assume that this electron is directly in line with the force and of the field. And so we need a few pieces of information, though. We're talking about an electron, so on your equation sheet, we have the charge of an electron. An electron's charge is equal to 1.6, you can call it a negative if you wish, negative 1.602176662 times 10 to the negative 19. All right, and if you recall from chemistry, Millikan was one of the first to calculate this charge, and he did it with the oil drop experiment and was really accurate for his day and age, or in the early 1900s, and it was phenomenal. I love that experiment. If you get a chance, YouTube oil drop experiment, and you can see it and you can read about it. It's pretty spectacular. So this is coulombs, and guess what the charge on a proton is? We don't need it here, but guess what? A proton, it's got the same charge but opposite in sign. Okay. We also need the mass of an electron. The mass of an electron for us is 9.1. This is also on your equation sheet, by the way. 10 to the negative 31st kilograms. Very tiny. All right, so let's go from here. They want the acceleration of the electron. Okay. Well, you need this equation that we haven't really done yet. F equals EQ, where E is the electric field and Q is the charge. They got to play nice. Well, we need coulombs on our charge. Is it? Beautiful. Just fill in and solve. So it is simply 265 newtons per coulomb multiplied by our charge, which is 1.602 times 10 to the minus 19th coulombs. The coulombs cancel out, we're left with newtons. Beautiful. So what's our force? Our force is, for me, 4.2453 times 10 to the negative 17th newtons. So now this is a net force. So this is a net force. What do net forces cause? They cause accelerations. How? Through Newton's second law. So all you have to do now, our good old friend, F equals ma, and so we have 4.2453 times 10 to the minus 17th equals our mass, which is, check here, 9.109 times 10 to the minus 31st, and then here's an A. Please, please, please put this scientific notation in its own brackets, so when you divide, it divides by the whole quantity. You know, we've gone over that and over that, so don't get caught and have your exponents on your 10 to the power of be messed up. It will happen. It easily happens. You got to containerize this and divide by the whole quantity. So A equals, for me, 4.66 times 10 to the 13th, and our units are meters over seconds squared. That's what happens when you divide a newton by a kilogram. So meters over seconds squared. And there you go. There's part 1. Boom. Okay. Now let's go to the next part. It wants to know how long will it, if it goes for this long in this field, what speed will it have? Okay, well, and starts from rest. Oh, wow, that sounds like kinematics. Initial velocity equals 0. Our acceleration came from here. Final velocity we want to know. Time is 1.16 times 10 to the -8th seconds. Oh, okay. V final equals V initial plus AT. Excuse me. And we have V final equals 0 plus A, which is 4.66 times 10 to the to the 13th, times this tiny time of 1.16 times 10 to the -8th. Okay, and then we do that. The final is equal to 5.40 times 10 to the 5th meters per second, which is a very high speed. It is very high, but remember, it's a tiny particle. And actually, we can accelerate electrons in this way. It's only about, I think, a little less than 1% of the speed of light, maybe 2/3 of a percent of the speed of light, but the maximum cosmic velocity, speed limit. But in particle accelerators, we actually can make these go much, much faster. So we use magnets and accelerate these particles through running them through miles-long tubes sometimes, where we're just using these large electric fields to accelerate particles. It could be electrons, it could be other things, it could be charged atoms of different varieties. And then we slam them into things and see what we create. So, pretty awesome. Well, I'll see you on the next problem.